Hi everyone, this is Mrs. Jackson, and this is the last section on modeling in Chapter 2. And this is Part 2 video where we're going to be talking about a financial analysis using quadratic functions. Before we get into the specifics of this problem, let's talk a little bit about vocab in the financial world, specifically for a manufacturer or for a reseller. So the first vocab phrase that I'm going to talk about is revenue. Revenue is a fancy word for sales. And what that doesn't mean how much money you're making, but it is all the money that you're taking in when you sell a product. And so your total revenue or your total sales are going to be how many units you sold times the price per unit. So for example, if I was in business to sell t-shirts and I sold 10 t-shirts and each shirt was $5, then my revenue on that would be $50 or 5 times 10. You also have production costs. Now, if I were actually physically making those t-shirts, I would have some costs associated with them. But even if I bought them from somebody else and I was reselling them at a higher price, I'm going to have some costs associated. And my total costs are going to be, again, the quantity of units sold. This time you're going to multiply, instead of the price per unit, you're going to multiply by the cost per unit. And the total profit that you're going to make in this business is going to be those total sales or total revenue minus the costs. Unless you're working for a nonprofit business, every single business out there is trying to maximize the profit. And there's certainly many ways to maximize that profit. It may be to generate a lot more revenue, or it may be to really focus on lowering your costs. Either way, each business is different, and in general, all profit businesses really focus on both the revenue side and the cost side. All right, let's get into this particular problem here. So, we have a theater, and they're selling special event tickets at $10 per ticket to benefit a local charity. The theater can seat up to 1,000 people. So the first thing here I notice is that I have a typo. So this should be 1,000 people. And the manager of the theater expects to be able to sell all 1,000 seats for the event. To maximize the revenue for this event, a research company volunteered to do a survey, and this is generally key in most businesses. The marketing people really need to know what people are looking for in a product. But in this example, the survey is basically looking at what price per ticket are people willing to pay for. So what they found is the results showed that for each $1 increase, and that means $1 over the $10 ticket, for each $1 increase, 20 fewer tickets will be sold. So you're not filling the theater anymore with all 1,000 seats. For example, if you increased $1, in other words, sold each ticket for $11, they believe that they're going to sell 20 fewer seats out of the 1,000. If they increase the price $2 up to $12 per ticket, then they're going to shorten that 1,000 seats by 40, etc. So this is the scenario we're trying to model. So the goal of this analysis is to determine what price of a ticket is going to generate the most revenue. And so each of these letters here, A through H, are going to step us through that analysis one step at a time. Okay, so the first letter A here, let X represent the number of $1 price per ticket increases. So write an expression to represent the expected price per ticket. So the expected price per ticket is going to be the $10 plus $1 times X. Okay, so each ticket price, if X is 0, if we're not going to increase it by $1, then the price of the ticket would be $10. If we're going to increase it by $1, then you would plug in 1 for X, and the new ticket price is $11, etc. So this is price per ticket. Okay, I'm just going to abbreviate. All right, use the survey results to write an expression representing the possible number of tickets sold. So we know that if we sell the tickets for $10, in other words, we don't increase the price, the survey says that we can sell all seats, which is 1,000 seats. So our baseline is filling the theater at 1,000 seats or 1,000 tickets sold. However, for every $1 increase, we're going to drop that ticket sales by 20 seats. So we're going to say 20 times X here. If X is 0, again, we'll fill the theater at 1,000. If X is 1, we're going to drop our ticket sales by 20, etc. So this is the quantity of tickets sold in our model. All right, letter C. Using X as the number of $1 ticket price increases and the expression representing price per ticket, write the function R to represent the total revenue in terms of the number of $1 ticket price increase. As we see above, the revenue, R, equals the price per unit times the quantity sold. So if we substitute in our expressions here, algebraic expressions, the price per unit is going to be our 10 plus 1x. I'm going to shorten that to 10 plus x. And the quantity sold is going to be 1,000 minus 20x. Okay, now I want to rewrite this in standard form, and hopefully you're already seeing that this is a quadratic function. So I've got R equals 10, I'll go ahead and use my highlighter, 10 times 1,000. I'm going to distribute everything. 10 times 1,000 is 10,000. 10 times minus 20, or negative 20x, is minus 200x. X times 1,000 would be 1,000x. And x times negative 20x is going to be negative 20x squared. As soon as you see that x squared term, you know you've got a quadratic. I'm going to tidy this up a little bit and get it in standard form. So I've got negative 20x squared plus 800x plus 10,000. So this is our revenue model. And depending on each of those $1 increases, that's going to model what our expected revenue will be. Okay, so the question becomes, how many $1 ticket price increases can we afford that's going to maximize our revenue? So that's our question. And if we just kind of take a look at our function here, we have a downward facing parabola. So the maximum revenue is going to be at that vertex. So we're going to go ahead and try to calculate what our vertex is going to be for this function. And we know that our vertex is h and k. Let me put that here. H comma k. In this context, h is x, and that's our $1 increases. How many $1 increases? And k is going to be that revenue in dollars, so it's dollar out. I'll just put revenue here. So our vertex is going to be h equals negative b over 2a. H equals negative 800 divided by 2 times negative 20. And 2 times negative 20 is going to be negative 40. And so if we look at what this results in, we've got 20. So in this context, we just solved for the number of $1 increases that our marketing people tell us are going to help maximize our revenue. So $20 increase on top of the $10. So that leads right into the next question, which is, what is the price of the ticket that's going to maximize our revenue? Our model says that the price per ticket is going to be 10 plus x, and we just solved for x. So our price per ticket is $30 per ticket is going to maximize our revenue. Now, what is that revenue when we sell $30 per ticket? We know we're not going to fill the theater. We're going to sell a lot less seats, but we're going to bring in more money. We're going to use our function and we're going to substitute in to solve for the output. Now, you may be tempted to substitute in 30 here for our X, but remember this X does not represent the price per ticket. It represents the number of $1 increases over our $10. So the number that we're going to be substituting in here for X is going to be that 20. So when we zoom in here, do recall that. Okay, so we've got our revenue equals negative 20x squared plus 800x plus 10,000. And now we're going to substitute in 20 for x. We've got negative 20 times 20 squared plus 800 times 20 plus 10,000. And I'm going to move over here. I've got negative 20 times 400 plus 800 times 20 plus 10,000. And this all simplifies to a total of $18,000 in revenue. Another way to think about this is in terms of the vertex. Our vertex is our maximum point on this function, h comma k, and our h is 20 $1 increases over the $10, and our output is 18,000. That's our vertex. Okay. So how many tickets will the theater sell to reach this maximum revenue? We know it's not going to be the 1,000. We're going to be taking several seats out. So our model for the number of seats sold is 1,000 minus 20 times x. In this case, we're increasing by $21, not $21, but $21 increases, I should say. And so we have 1,000 minus 400. So our total seats that we're going to fill is going to be 600 seats, or 600 tickets sold. Okay, so ultimately, what did that do for our charity? How much more money did the theater make for the charity by increasing the ticket price, at the expense of selling less seats? If you look at the dollars and cents of it, the original plan was to sell 1,000 seats at $10 per ticket, giving us $10,000 in revenue. The new plan has us selling 600 tickets at $30 a ticket, giving us $18,000 in revenue. Pretty big jump. So ultimately, for our charity, our improvement is $8,000 in additional revenue for our charity. That's a lot. The entire plan, however, rides on how good your marketing people are. So in all areas of business, these surveys are critically important because they really have a huge impact on profit and loss. In any case, you have an example, as I mentioned in class today. Apple is a prime example in today's consumer marketplace, where they came in and really disrupted an entire industry. The cell phone industry was well into 15 years of business, where all the manufacturers were competing with each other to lower the price of their unit, Apple came in and did exactly the opposite. They increased the price of the unit, tried to make something compelling that people would buy, and they were okay selling lower volume in the beginning. Ultimately, they took over the entire market. So the moral of the story is you have to have good marketing, and more is not always an increase in profit. That's for sure. Okay, I hope this video and the one before it helps you see that quadratic functions are all around us. We need them to model all kinds of real-world applications. Thanks for listening. Please subscribe.